Welcome back to the deep dive. Today we are moving from the merely complicated to the truly cosmic,
We're staring straight into the abyss.
straight into the heart of the universe's most extreme objects, black holes. And this isn't just about massive gravity.
Not at all. It's really about the ultimate challenge to physics itself.
Yeah.
It forces us to try and unify the rules of the very, very large
General relativity.
with the rules of the very, very small. Quantum mechanics.
We've put together a pretty formidable stack of sources for you today.
We're going to be covering everything from the classical predictions to the hard-won observational triumphs.
And then into the really radical quantum theories and critically the ongoing theoretical wars.
Oh yeah, the information paradox, the firewall paradox. These are battles being waged right on the very edge of space-time.
So our mission today is to give you the shortcut, the real guide to understanding why black holes aren't just, cosmic vacuum cleaners.
There's so much more. They're the single most important laboratory we have for testing physics beyond Einstein.
We're decoding the universe's ultimate mystery.
And if there's one single concept that really defines our entire discussion today, the one boundary that separates the known from the impossible.
It has to be the event horizon.
It's the event horizon.
It's such a dramatic name. I mean, we've all heard the phrase boundary of no escape, but what exactly is it, mathematically speaking?
It's the surface of last light. It's that region of space-time where the gravitational pull gets so intense that the escape velocity actually equals the speed of light.
So nothing can get out.
Nothing. Anything that crosses that barrier is permanently, absolutely sealed off from the rest of the universe. It's a fundamental prediction of Einstein's general theory of relativity.
And the most mind-bending feature, the one that really sets up all the major paradoxes we'll get into later, is that crossing it is locally totally uneventful.
That is the critical piece of the puzzle. General relativity predicts that for an observer falling in, we call him the free-falling observer, space-time locally is perfectly smooth. Their clock ticks normally. They feel no singular behavior, no wall, no flash of light.
They just drift right across.
They just drift across. This concept, it's often called no drama, and it means they are completely unaware that they've just passed the point of no return.
So they only realize their fate once they start accelerating towards the singularity inside, but the moment of crossing itself is, it's indistinguishable from just floating in empty space.
And we'll see how fiercely that no drama idea is being challenged by quantum mechanics a little later on.
Okay, so to really understand the crises that are happening in physics today, we have to start at the foundation.
We have to. And that foundation is Einstein's general theory of relativity, or GR, from 1915.
This wasn't just a small step up from Newton, was it?
Oh no, it was a complete conceptual revolution. It explained gravity not as a force, but as the geometry of the universe itself.
So matter and energy warp space-time.
And that warped geometry then dictates how everything else moves. That principle is the absolute bedrock of all modern black hole physics.
But the journey from, the theory on paper to accepting black holes as real objects was surprisingly long. And skeptical.
Incredibly skeptical. The first major step forward happened almost immediately, though. Just months after Einstein published his equations.
And this was Karl Schwarzschild?
Karl Schwarzschild, a German physicist who was serving on the Russian front during World War I.
That's just astonishing timing, considering the context.
It's unbelievable.
Yeah.
And he found the first exact, non-trivial solution to Einstein's equations.
So what did his solution tell us? What was the big reveal?
Well, his solution assumed the absolute simplest case, a perfectly spherical, non-rotating, uncharged mass.
Okay, a very idealized object.
Very. And it revealed a critical radius, which we now call the Schwarzschild radius. Mathematically, at this specific radius, certain terms in the metric, the math that describes spacetime,
Right.
they became singular. They went to infinity.
So the math was screaming that something wild was happening there, but physicists didn't quite get what that meant physically yet.
Not at all. They saw an infinity and just assumed the math was broken at that point.
A mathematical quirk, not a real place.
Exactly. For decades, the Schwarzschild radius was just seen as a weird artifact. There was massive skepticism that anything could compress itself down that far.
You mentioned Arthur Eddington.
Yes, a physicist who was famous for actually proving general relativity during the 1919 eclipse. He discussed the idea in 1926, but dismissed it. He said it was, and this is a quote, Too ridiculous for a star to exist at that limit.
And if the people who confirmed GR were that skeptical, I can only imagine how Einstein himself felt. I find it fascinating that the architect of the whole theory actively tried to shut down the idea of black holes.
He really did. In 1939, Einstein published a paper trying to prove that gravitational collapse was physically impossible.
What was his argument?
It focused on static pressure. He claimed that as a star shrinks, the increasing pressure or, the angular momentum from its rotation would always prevent the material from collapsing below that critical Schwarzschild radius.
So he was basically looking at the problem like it was a normal star, held in a stable balance.
Precisely. He was looking at a static configuration, and because of that, he missed the key ingredient.
Dynamics.
Dynamics. He just didn't account for the possibility of a star simply imploding under its own momentum after its internal furnace died out.
Which is where the modern model literally burst onto the scene, solving the very problem Einstein thought was unsolvable.
And in the very same year that he published his critique.
Incredible.
Also in 1939, you have the American physicists Robert Oppenheimer and his student Hartland Snyder.
Oppenheimer, later of atomic bomb fame.
The very same. They solved Einstein's equations for that dynamic scenario, an idealized imploding star. And this, the Oppenheimer-Snyder model, is truly the birth certificate of the black hole concept as we understand it.
Okay, let's unpack this model, because this is where the time dilation and the sheer observational weirdness really begins for you, the person watching from the outside.
Their calculations showed that the fate of the star is perceived entirely differently depending on your viewpoint.
So it really matters where you're watching from.
A huge amount. For the stellar material collapsing inward, the collapse is finite. It's rapid. From their perspective, they reach the singularity in a very short amount of time.
But for the faraway viewer watching this whole thing happen,
For the external observer, the picture's completely different. And this is all due to general relativity's effects on time and light. As the star collapses towards the Schwarzschild radius, two effects just ramp up dramatically.
okay, what are they?
First, gravitational time dilation accelerates. Time appears to slow down on the star's surface relative to the observer.
And second.
Second, the light being emitted from the star gets more and more redshifted.
So the light waves are getting stretched out as they fight their way out of that intense gravity well.
Exactly. So by the time the stellar material actually reaches the critical radius, the time dilation is infinite, and the light is infinitely redshifted.
Which means that, to us, the faraway observer, the implosion just seems to slow down and then freeze.
It freezes in time, right at that critical radius, and then it fades away into infinite dimness.
So the star never truly disappears from our perspective. It just becomes a frozen, infinitely dark ghost of its former self. It basically defines the boundary of the event horizon itself.
That's why we say the formation of the event horizon is a process that takes an infinite amount of time for the external observer, even though it's, instantaneous for the infalling matter.
Okay, so once that collapse has happened, let's talk about the interior geometry. General relativity says everything inside that horizon leads inexorably to one place.
The singularity.
And that's the part where the physics just breaks down, right?
Yeah.
The point of infinite density and zero size.
Precisely. The singularity is where the curvature of space-time becomes infinite, and all geodesics, that's all the paths of freely falling objects, they just terminate there.
Classical GR insists every black hole has to have one.
It does. But the point where your math gives you infinities usually just signals a breakdown of the theory itself. Most physicists today believe the singularity is where GR has to give way to a complete theory of quantum gravity.
So whether a true zero-volume point singularity exists in nature is one of the deepest questions we face.
Absolutely.
And what happens during the approach to that point is the stuff of nightmares. Spaghettification.
Ah, the noodle effect.
Tell us why this is so horrifyingly effective.
It's all about tidal forces.
Yeah.
Gravity isn't uniform, not even over short distances. For a large, simple black hole, the tidal forces, that's the difference in gravitational pull between, say, your head and your feet.
Okay.
And the lateral squeeze on your shoulders, they become enormous.
So if I were falling feet first, my feet would feel a much, much stronger gravitational pull than my head.
Correct. The differential force stretches you vertically and compresses you laterally. As you get closer to the singularity, these tidal forces grow exponentially.
And they eventually become stronger than the forces holding your own body together.
Stronger than the atomic forces. You are torn apart, atom by atom, into a long, thin stream of plasma, a noodle, before that matter is finally crushed into the singularity.
It sounds truly awful, though I did hear that if the black hole is supermassive, the spaghettification actually happens inside the event horizon.
That's a great distinction to make. It's true.
So it gives the infalling astronaut a few peaceful moments of no drama before the crushing begins.
Right, because the tidal forces grow as 1 over the radius cubed. So for a stellar mass black hole, those forces are lethal before you even cross the horizon.
But for a supermassive black hole in SMBH, the horizon is so vast that the gradient of gravity is much gentler right at the boundary.
It is. It allows that no-drama entry to hold true for a little while before the tidal forces eventually win out deep inside.
Okay, so if the tidal forces are tearing you apart internally, let's pull back out to the region where matter, specifically light, still has a tenuous grasp on freedom.
The photon sphere. The photon sphere is a fascinating region just outside the event horizon. Here, gravity is so strong that photons, particles of light, can actually orbit the black hole.
So it's where light can still escape, but only if it's traveling perfectly outward.
Exactly. And if a photon enters this sphere on a critical trajectory, its path will curve completely around the black hole, locking it into an unstable circular orbit.
So if you were floating near a black hole and you shine a laser towards the photon sphere,
And you hit the exact right spot.
that light would circle the black hole and come back and hit you in the back of the head.
It would. It acts like a kind of cosmic mirror.
And I understand the radius of this photon sphere is one of the features that changes based on the black hole's 3 defining characteristics, which we're about to get to.
Yes. For a non-rotating black hole, it's at 1.5 times the Schwarzschild radius. But crucially, for rotating or charged black holes, that radius changes. Well, the radius shrinks if the black hole has a high electric charge, for instance. For a spinning black hole, it's closer on one side and farther away on the other. It's highly sensitive to the black hole's geometry.
So we've established the theoretical framework, but now let's look at the incredible variety of black holes we actually see out there in the universe.
They all form through gravitational collapse, but we categorize them pretty dramatically by size.
The formation story generally begins with a massive star collapsing at the end of its life.
Right, either through a direct collapse or after a supernova explosion. And this leads to the most common type we see: stellar black holes.
These are typically the remnants of stars maybe 8 times the mass of our sun or larger. We observe them up to, 25 or more solar masses?
That's Cygnus X1, the first one confirmed, is a classic example.
And moving up in size from there, we have the still mysterious intermediate mass black holes, IMBHs.
These range from 100 up to 100,000 solar masses. They're considered much, much rarer, and their formation mechanism is still really heavily debated.
Why are they so tricky? If we can see the small ones and the huge ones, why is this middle ground so elusive?
Because the standard formation paths just don't easily produce them. They might form in the dense, chaotic environments of globular star clusters, maybe through runaway stellar collisions,
Or mergers?
or perhaps the merger of many smaller black holes. Our clearest evidence for them actually comes from gravitational wave astronomy.
From LIGO.
Exactly.
Yeah.
LIGO has detected several black hole mergers in that 100 to 350 solar mass range, confirming that these heavy but not supermassive objects absolutely exist.
And then the true monsters, the ones that anchor the very fabric of galaxies.
The supermassive black holes, or SMBHs, millions or even billions of solar masses.
And we find them nestled in the centers of, well, basically every large galaxy, including our own Sagittarius A star.
We do. And their formation is still one of the greatest puzzles in cosmology. How did these behemoths grow so large so early in the universe's history?
What are the leading theories?
They might have grown by relentlessly absorbing surrounding stars and gas, or by merging with other black holes during galactic collisions. Or, and this is a really interesting idea, by the direct collapse of vast, pristine gas clouds in the early universe, skipping the whole stellar phase entirely.
Regardless of how they start, once a black hole settles down, it becomes featureless, incredibly simple.
And that brings us to this very counterintuitive rule of the cosmos, the no-hair theorem.
This is where it gets really interesting. Tell us why this is such a profound concept.
The no-hair theorem, and the hair there just refers to any distinguishing features, is a critical conjecture in black hole physics.
Okay.
It states that once it's stable, a black hole is completely defined by only 3 physical parameters.
Just 3.
Just 3. Mass, electric charge, and angular momentum, or spin. That's it. All the incredible complexity of the star that collapsed, its composition, its magnetic fields, all of that is erased forever. The black hole is a nearly perfect object.
So the black hole truly forgets everything that fell into it except for those three numbers.
Right.
Why are those the only three things that survive the cosmic blender?
Because those three quantities are fundamentally conserved in the universe. Mass energy is conserved, electric charge is conserved, and angular momentum is conserved. And since a black hole interacts with the rest of the universe, primarily through gravity and electromagnetism, those are the only properties it can retain.
Okay, let's break those down. Mass is easy. We determine that by watching how things orbit around it. What about charge?
Charge is theoretically possible. And mathematically, a charge can reduce the black hole's diameter by up to 38% compared to an uncharged one of the same mass.
But do we actually see charged black holes?
Probably not. Most are believed to be virtually neutral in the real universe.
Why is that?
It's a self-correcting problem. If a black hole develops a net positive charge, it'll just quickly attract and pull in enough free electrons from the surrounding cosmic plasma to neutralize itself.
And the same if it's negative.
The same happens if it's negatively charged. It repels electrons until equilibrium is restored. For the most part, we expect the charge, Q, to be near zero.
Which leaves spin J as the truly dynamic variable, and it's essential for generating the immense power we see from black holes.
Absolutely. The universe is full of spinning objects, and angular momentum is conserved. So when a massive spinning star collapses, the remnant black hole inherits that spin and often accelerates it wildly.
We found some spinning incredibly fast, right?
Oh yeah, GRS 1915 plus 105 spins at over 1,000 revolutions per second, which is approaching the theoretical maximum speed. Even Sagittarius A star rotates at about 90% of the max rate.
Wait a minute, how do you measure the spin of something that is, by definition, featureless and invisible?
It's inferred through its interaction with the gas closest to it, specifically the accretion disk.
Okay.
Gas plunging towards the black hole forms this disk that gets extremely hot, and it emits high-energy X-rays. Due to general relativity, there's a minimum stable orbit for matter before it just plunges inward.
And that minimum radius depends on the spin.
Critically, if the black hole spins faster, the stable orbit moves closer to the event horizon.
So you can measure the spin by looking at how close the matter gets.
Correct. By analyzing the relativistic redshift of the X-ray emission lines from that gas, specifically the iron K alpha line astronomers can map the inner edge of the accretion disk. This geometric measurement allows them to accurately determine the black hole's angular momentum.
So spin, or angular momentum, is clearly this massive engine for cosmic power, which leads us straight into the staggering phenomena of accretion disks and relativistic jets.
The accretion disk is the black hole's engine room. Gas, dust, even stars falling toward the black hole flatten into this massive superheated disk because of angular momentum.
And friction within the disk heats it up.
Right. Internal turbulence caused by magnetic fields heats the inner regions to millions of Kelvin, releasing an immense flux of X-rays and sometimes visible light.
And the efficiency of this process is what's truly staggering, far beyond what we see in stars.
Oh, it's not even close. Compared to nuclear fusion, where only about 0.7% of hydrogen mass is converted to energy, the accretion process is immensely efficient.
How efficient are we talking?
In the innermost regions, you can get up to 32% of the infalling matter's mass converted into raw energy for a maximally spinning black hole.
Yeah.
This is why they're capable of powering some of the brightest objects in the cosmos.
And sometimes, instead of the matter just plunging in, we see these incredibly narrow, blinding beams of plasma shooting away.
The relativistic jets.
Right.
These are streams of highly magnetized plasma, accelerated away from the poles along the black hole's rotation axis. They travel at fractional speeds of light, sometimes over 1/10 the speed of light.
And they are associated specifically with spinning black holes.
Spinning black holes that have strongly magnetized accretion disks, yes.
What's the best explanation we have for how a black hole, an object famous for absorbing everything, can launch these incredible amounts of energy away from itself?
There are two leading theoretical mechanisms. The first is the Blandford-Znajek process.
Okay.
This focuses on the magnetic field lines. If the black hole is spinning and magnetic field lines are threading the event horizon, the black hole's rotation literally drags those magnetic field lines around.
Like a giant dynamo.
Exactly like a giant dynamo. It twists the field lines and launches the plasma perpendicularly away from the disk. It's essentially extracting rotational energy from the disk.
And the second proposed mechanism extracts energy from the black hole itself.
That's the Penrose process. It's mathematically complex, and it requires specific conditions in the ergosphere around a rotating black hole.
The ergosphere being the region where space-time itself is dragged around by the spin.
Correct. And the basic idea is that rotational energy can be extracted from the black hole. A particle can split, one fragment falls in, and the other escapes carrying away more energy than the initial particle had.
Effectively slowing the black hole's rotation down.
Precisely.
And the sheer size of the jet producers determines what we call them, right?
Yes. Supermassive black holes actively fueling these jets are called quasars. They're the luminous cores of distant galaxies.
And their smaller cousins.
Their stellar mass counterparts found here in the Milky Way are called microquasars.
All these effects, the gravity, the jets, the massive X-ray fluxes, these provide the vital, indirect evidence we used for decades to confirm that black holes exist. Let's run through the observational milestones.
We have to start with Cygnus X1, confirmed in 1972 after years of intense scientific debate.
It was an X-ray source.
An intense X-ray source in a binary system with a Supergian star. By observing the star's orbital period and velocity, astronomers were able to calculate the mass of the unseen companion.
And that mass calculation was the key because it was just too large for anything else.
Exactly. The unseen companion's mass was calculated to be significantly greater than 3 solar masses, which is the theoretical maximum limit for a neutron star.
And since it wasn't shining,
Since it emitted no visible light, the only logical conclusion was that it was a black hole. This was the first strong candidate confirmation.
then the story of Sagittarius A star, the supermassive black hole at the center of our own galaxy.
This is one of the great success stories of modern observational astronomy.
Largely driven by Andrea Ghez and Reinhard Genzel.
Yes, since 1995, they and their teams have meticulously tracked the Keplerian orbits of nearly 90 stars very close to the galactic center, especially the star S2.
S2 whips around the center every 16 years, right?
It does. And by tracing those elliptical orbits, they could use basic physics to infer the mass and location of that central gravitational anchor.
And the numbers were just immense.
A gargantuan mass of 4.3 million solar masses, concentrated within a radius so tiny that only a supermassive black hole could fit the bill.
Which was then stunningly confirmed visually in 2022 by the Event Horizon Telescope.
That image of Stellar A-star shadow was a beautiful testament to the geometry predicted by general relativity.
Beyond X-rays and star tracking, we've now entered the age of direct space-time detection.
Gravitational waves, GWs.
Yeah.
The detection of gravitational waves by LIGO revolutionized our understanding of black holes. Events like GW 15091 the first detection in 2015.
That was the merger of two black holes.
2 stellar mass black holes, 36 and 29 solar masses, merging into a single 62 solar mass remnant. And the remaining 3 solar masses were just radiated away as pure gravitational energy.
So this provided two crucial pieces of evidence. It proves stellar mass black holes exist in binaries, and that they can be much bigger than we previously thought.
Exactly. And finally, there's a technique to detect the truly isolated black holes, the loners that aren't eating or merging, and so they remain invisible.
Microlensing.
Microlensing, where the black hole's gravity acts like a powerful telescope lens,
So it passes in front of a background star.
and its gravity focuses the star's light, causing a temporary, precise brightening of that background star. This effect, though it's very subtle, allowed astronomers in 2022 to confirm the mass of the first isolated black hole,
How big was it?
measured at about 7 solar masses. It demonstrated that there is a vast, uncounted population of these things in the galaxy.
So general relativity works. Observations confirm black holes are real, but now we enter the realm where gravity meets the quantum world, and this is where the picture gets radically complicated.
This all starts with black hole thermodynamics.
Right.
When physicists started applying thermodynamic laws to black holes in the early 1970s, it created a massive paradox. Classically, a black hole has 0 entropy. It was a perfect, ordered object.
But if you throw something with high entropy, like a cup of coffee, into a black hole,
You seem to violate the second law of thermodynamics, which states that total entropy in the universe must always increase,
so in 1972, Jacob Bekenstein proposed that black holes must have entropy.
and that this entropy must be proportional to their surface area.
Famously, Stephen Hawking was one of his strongest opponents at first.
He was. Hawking argued that if a black hole had temperature and entropy, it must be able to radiate energy. But general relativity explicitly forbids anything from leaving the event horizon.
But then, Hawking had his own monumental breakthrough in 1974.
He did. uniting quantum field theory with general relativity, and he predicted that black holes must radiate.
Hawking radiation.
That's the one. It resolved the conflict, and it completed the thermodynamic analogy. Mass relates to energy, surface gravity relates to temperature, and the black hole's surface area relates to its entropy.
This formalized the Bekenstein-Hawking entropy formula, S equals A over 4.
A beautifully simple equation.
And it's profound. It suggests that the vast amount of information required to define the black hole, its internal state, its entropy, can be entirely encoded on its two-dimensional boundary surface.
It's an early, powerful hint of what we now call the holographic principle, the idea that the physical description of a volume of space might be encoded on a bounding surface.
It links geometry, the area, with information, the entropy, in a way classical physics never could.
Never.
Now let's drill down into the mechanics. How does the actual emission process work? It relies on effects just outside the horizon.
Specifically, the Unruh effect.
Okay, let's set the scene carefully.
So quantum field theory tells us that space is not truly empty. Particle-antiparticle pairs are constantly popping into and out of existence in the vacuum. We call them virtual particles.
Right.
The Unruh effect states that the definition of a vacuum is observer-dependent.
Explain that crucial distinction.
If you are floating inertially in flat space, you see a vacuum. However, the Unruh effect predicts that an accelerating observer will detect a thermal bath of these particles. They will see energy being radiated.
And how does that relate to a black hole?
Near the event horizon, we have two types of observers. The free-falling observer, the FRIFO, is inertial. They experience no drama.
But the static observer,
The FIDO, who has fired their rockets constantly to hover in place just outside the horizon, is accelerating tremendously to resist the gravitational pull.
and that acceleration causes the FIDO to perceive a thermal bath of particles?
That is the Unruh effect at the horizon.
And Hawking radiation is the consistency requirement that ties that localized thermal bath to the entire universe.
Precisely. Hawking radiation is the ultimate result of this near-horizon quantum dynamics, where the extreme gravitational gradient tears one particle of a pair into the black hole and allows the other to escape to infinity.
And crucially, you said the Unruh effect is a thermal bath with no net energy flux. But Hawking radiation does have a net energy flux.
That's the key distinction. The Unruh effect describes a local temperature caused by acceleration in flat spacetime with no overall flow of energy. Hawking radiation, however, describes a situation where the curved spacetime at the horizon is so extreme that it produces a net outward flux of positive energy.
And that flux effectively drains the black hole of mass via E equals mc squared.
It does. This net flux is what causes evaporation and lifespan.
And this is where the sheer, incomprehensible scale of cosmic time really hits you.
The key parameter is the black hole's temperature. The Hawking temperature is inversely proportional to its mass.
So bigger black holes are colder.
Much, much colder.
Let's talk numbers here, because this leads to that incredible conclusion that stellar black holes aren't evaporating at all right now.
A stellar black hole of 3 solar masses has a temperature of only about 10 to the minus 7 Kelvin.
Which is very cold.
Extremely cold. The universe is filled with the cosmic microwave background, the CMB, which is leftover heat from the Big Bang, and it's currently measured at 2.7 Kelvin.
So 10 to the minus 7 is far, far colder than 2.7.
Dramatically colder. And since the black hole is colder than the space around it, it is currently absorbing more energy from the CMB and interstellar dust than it's radiating away.
So all currently existing stellar and supermassive black holes are actually growing, not shrinking.
That's right. They will only start to evaporate when the universe has cooled down to below their temperature, which is billions, perhaps trillions of years in the future.
So the only objects that might be actively shrinking are the hypothetical ones formed in the earliest, hottest bolts of the universe.
The primordial black holes. Only those formed in the early universe, with masses less than about 10 to the 12 kilograms, less than 1% of Earth's mass, would have had temperatures high enough to have fully evaporated by now.
And they would end in a flash.
A violent burst of gamma rays.
And for the massive ones, the lifespan is just ludicrous. A solar mass black hole lasts 10 to the 67 years.
That's a 1 followed by 67 zeros. To put that into context, the current age of the universe is about 1.38 times 10 to the 10 years.
It's not even close.
And the monster black holes. A 10 to the 14 solar mass supermassive black hole might last up to 2 times 10 to the 106 years. These figures just demonstrate that black hole evaporation is a process far beyond any timescale we can meaningfully grasp.
Before we jump into the full-blown paradoxes, we have to mention the inherent flaw that Hawking's initial brilliant calculation carried.
The Transplanckian problem. This is a deep conceptual issue with the derivation itself. When Hawking calculated the radiation, he modeled it as virtual particle pairs that start arbitrarily close to the horizon.
Okay.
To trace the wavelength of the escaping particle back to its origin, the calculation requires that the particle must have had an infinite frequency,
And therefore a wavelength shorter than the Planck length.
a Transplanckian wavelength.
Yeah.
And the Planck length is the scale where space-time itself is thought to become foamy and turbulent, where all our current laws of physics completely break down.
So the calculation relies on physics operating at a scale where we know our current physics is fundamentally wrong.
Exactly. It suggests that any complete theory of quantum gravity must provide the correct starting point for those particles near the horizon. Otherwise, the entire derivation of Hawking radiation is, theoretically problematic.
And this brings us to the core conflict that has driven theoretical physics for the last 5 decades. The black hole is the only place in the universe where we are forced to confront the incompatibility of our two most powerful theories.
General relativity and quantum mechanics.
Let's start with the big one, the black hole information paradox.
The paradox is a direct conflict between the validity of semi-classical gravity, that's Hawking's prediction, and the most fundamental requirement of quantum mechanics.
Which is that it must be unitary.
It must be unitary.
Let's slow down on unitary. Why is that so crucial to physics?
Unitarity just means that all quantum processes are reversible. Information is conserved. The total amount of information in a system can never decrease over time.
So if you know the state of the system now, you can, in principle, perfectly determine its state at any time in the past or the future.
That's it.
So using the classic fire analogy, if you burn a notepad, the paper is reduced to ash and gas, but the information, the message written on it, is theoretically still there.
It is. It's in the exact quantum state of every single molecule of smoke and ash.
Yeah.
In principle, if you had a powerful enough quantum computer, you could track every particle and revert the process, recreating the original message.
But Hawking's calculation of black hole evaporation means this theoretical reversibility is impossible for black holes.
It does.
How so?
Because Hawking radiation is thermal and it's random. It depends only on the black hole's mass, spin, and charge. Its 3 features. It's indistinguishable.
So if you form a black hole from a stack of highly ordered physics textbooks,
And then you form an identical black hole from a cloud of disordered interstellar gas.
they will evaporate and release the exact same stream of thermal random radiation.
Exactly the same. The radiation carries no specific information about the composition of what fell in. The information about the textbooks is seemingly gone forever.
And that leads to a catastrophic loss of determinism.
It does. If the information is truly lost, then even if you knew the exact quantum state of the universe after the black hole evaporated, you couldn't trace the past and determine the state of the universe before the collapse.
So this violates unitarity.
And there's no known process in the universe other than black hole evaporation where determinism is lost in this way.
So the community was faced with this stark, unappealing choice. Either physics is non-deterministic, or strong quantum gravity effects must apply to regions of low curvature where GR is supposed to be perfectly reliable.
And that search for a resolution led to the invention of an even sharper conflict in 2012, the firewall paradox.
This is where physicists sought to prove that if you assume unitarity is true, the equivalence principle must fail right at the horizon.
Exactly.
It's a complex thought experiment. Let's carefully outline the 4 postulates that create this contradiction.
The 4 assumptions are: 1, unitarity, information is conserved. 2, the semi-classical approximation, Hawking radiation is real. 3, the central dogma, black hole entropy is a real complex thing. And 4,
No drama.
no drama, the equivalence principle. The free-falling observer notices absolutely nothing unusual crossing the horizon.
Now, here is where the quantum conflict arises.
It centers on a single Hawking particle, B, emitted just outside the horizon, and its infalling partner, A. They're created as an entangled pair from the vacuum.
So, for no drama to hold, B must be maximally entangled with A.
It must be. That's a basic requirement of quantum field theory near the horizon. But now let's introduce the third participant,
Yeah.
the early radiation R, that escaped long ago.
Okay.
For unitarity to hold meaning, information is conserved and can eventually be decoded. Particle B must also be maximally entangled with all that previous radiation, R, that has escaped.
So particle B needs to be maximally entangled with particle A, for no drama, and it needs to be maximally entangled with the entire escaping radiation R for unitarity.
And that is the contradiction. Quantum mechanics fundamentally forbids a single particle,
Yeah.
B, from being maximally entangled with two different independent systems, A and R, simultaneously.
The monogamy of entanglement.
That's the rule. So one of those four postulates has to fail.
And the resolution proposed by the firewall proponents was to sacrifice no drama.
If no drama is relaxed, the entanglement between A and B is violently broken at the horizon. The infalling observer hits a hot membrane, a wall of pure energy.
The firewall.
The firewall, right at the event horizon, destroying the smooth spacetime required by the equivalence principle.
That's a truly powerful argument. But I understand the critique has been sharpened even more recently. It suggests the problem exists even before you introduce the complication of unitarity.
Yes. This is a very interesting recent argument, which showed that the semi-classical approximation, postulate 2, and no drama, postulate 4, contradict each other by themselves.
How can the mere existence of Hawking radiation cause drama separate from the entanglement issues?
It hinges on the fact that the static observer, the Phaedo, hovering outside the black hole, observes an intense, high-frequency flux of Hawking radiation pouring outward from the horizon.
And since this radiation is energy, it must exert radiation pressure.
Like the subtle pressure solar wind exerts on a satellite. Exactly. From Phaedo's perspective, this outward radiation flux exerts a measurable pressure on a free-falling object, on the FRIFO. It slightly deviates it from its perfect inertial geodesic path.
But wait, a deviation from a geodesic is an observer-independent physical effect.
And that's the kicker. If Phaedo sees the FRIFO being pushed by radiation, the FRIFO must also experience that effect locally.
Even though the equivalence principle says they should feel nothing.
Exactly. The FRIFO should feel local acceleration or tidal forces from interacting with this high-energy radiation field right at the horizon. So if semi-classical Hawking radiation exists, it must cause drama for the infalling observer.
So the existence of the radiation itself makes the horizon a violent place.
Irrespective of the long-term fate of information.
Okay, if we agree there is a crisis, let's talk about the proposed solutions that completely rewrite the geometry of the black hole. First, the radical fuzzball hypothesis from string theory.
The fuzzball hypothesis is a genuine attempt to resolve the information paradox using a framework that naturally incorporates quantum gravity.
And it argues that the black hole is not an empty void surrounding a singularity.
Not at all. It's proposed to be a ball of the ultimate form of degenerate matter, a dense, chaotic tangle of strings and brains. And it has a physical surface located precisely at the radius predicted for the event horizon.
So there's no singularity inside and no empty void. It's structure all the way through.
Correct.
So instead of crossing an empty, smooth horizon, infalling matter hits a physical, fuzzy surface. How does this resolve the paradox?
Because the surface has physical structure, the quantum information of the infalling matter is not lost. It's absorbed and encoded onto the surface of the fuzzball, which functions like a massive, highly complex quantum computer memory bank.
So no zero-volume singularity to crush the information, unitarity is maintained.
And the paradox is resolved. The fuzzball essentially is the quantum mechanical microstate of the black hole.
That sounds like a radical rewrite of reality. But I remember that incredible counterintuitive statistic about the density of these fuzzballs.
It's one of the most surprising nuggets from our sources. You intuitively assume a more massive black hole means a denser object.
Right.
But because the radius scales linearly with mass, while the volume scales cubically, the mean density of a black hole actually decreases as the inverse square of its mass.
So for a stellar mass black hole, say 10 solar masses, a fuzzball would be incredibly dense, like a neutron star.
Yes, extreme density. But the massive, supermassive black hole, Sagittarius A star, which is 4.3 million solar masses.
It's much less dense.
Its average density would be only about 51 times that of solid gold. The sheer volume makes it less dense internally.
51 times the density of gold for a 4.3 million solar mass object? That's incredible. And if you calculate an even larger one,
its mean density would be equal to the density of Earth's atmosphere at sea level. Imagine a cloud of matter, light as air, yet so massive that light cannot escape. That is the bizarre implication of the fuzzball hypothesis.
That's a great takeaway, but if the fuzzball is purely theoretical, how can we possibly test it?
The path to testability runs through gravitational wave astronomy. The classical black hole, being a singularity in a void, has a specific response when it merges. We call it the ring-down phase.
But a fuzzball is an extended object with physical structure.
Right. It's like comparing a classical bell to a damp, fuzzy ball. They will ring differently when struck.
So the gravitational wave signal would be different.
Simulations suggest that when two fuzzballs merge, the resulting signal might display subtle deviations from the general relativity prediction. We might see slower decay rates and potentially unique delayed echoes caused by the waves interacting with the physical fuzzy surface.
So we need better detectors.
Future detectors like LISA, which are designed to observe massive binary mergers, are expected to significantly improve our ability to detect these unique fuzzball attributes.
Okay, moving to the most recent conceptual breakthrough, which provided an alternate path to resolving the information paradox without invoking new physical objects like fuzzballs.
The Page curve and the quantum extremal surface.
A major turning point around 2019.
It was. It showed that information is conserved if we use a different semi-classical analysis. The theoretical prediction by physicist Don Page suggests that if unitarity is true, the entropy of the Hawking radiation should follow a specific shape over time.
The Page curve. The entropy starts at 0, increases as the black hole evaporates, but then must decrease back to 0 once the black hole is fully gone.
Showing all information was eventually returned. But Hawking's original calculation showed the entropy just increasing forever, implying information loss.
So what was the breakthrough?
Applying a formula developed earlier, the quantum extremal surface, or QES formula, instead of the traditional Hawking calculation. This new formula incorporates corrections derived from quantum gravity effects into the calculation of space-time geometry.
So the physicists weren't breaking general relativity, they were just using the wrong equation for the problem.
That's the interpretation. The QES formula is the mathematically correct tool for calculating entropy in systems of immense complexity, and when used, it reproduced the exact shape of the Page curve.
So it satisfies unitarity.
And the information paradox, at least in this semi-classical setting, was resolved.
This suggests a new governing principle. The reason these new quantum-derived rules are required for black holes, but not for, say, the orbital path of Mars, isn't just high curvature.
It's something else entirely.
Complexity.
That something else is complexity. The physics of the solar system is accurately described by classical geometry because it's a simple system in terms of information density. A black hole, by contrast, is a staggeringly complex quantum system.
How complex are we talking?
Researchers have estimated that decoding the information contained in the radiation from a single solar mass black hole would require a quantum computer circuit whose size is exponential in 10 to the 77.
Wow.
That complexity, the sheer density of encoded information, is what triggers the need for the specialized QES formula and fundamentally quantum-derived rules.
So the message from the Page curve breakthrough is that classical general relativity doesn't just break down at high curvature at the singularity. It breaks down at high complexity right at the horizon.
Exactly. This is the new, nuanced principle emerging from the paradoxes.
Yeah.
It suggests that the division between classical and quantum gravity effects is based on information density, not just physical location or gravitational strength.
What an incredible journey we've taken. I mean, starting from Einstein's initial skepticism and the forgotten solutions of Schwarzschild and Oppenheimer, right up to the modern era of gravitational waves and quantum paradoxes.
This deep dive really reveals that the event horizon, once thought to be a simple, featureless boundary, is actually the front line of the war between physics' greatest theories.
And we've established that the existence of Hawking radiation forces drama upon the infalling observer, challenging that long-held equivalence principle.
And the most promising resolutions, from the fuzzball hypothesis to the success of the quantum extremal surface formula, they all point away from classical geometry and toward a new paradigm that's defined by information.
If the new models are correct, the trigger that demands new, exotic physics is the object's complexity. Its ability to encode vast amounts of information, not just the physical strength of the gravitational field.
And so you, the listener, now understand why the black hole information paradox is the crucial guiding post for finally achieving a unified theory of quantum gravity.
The ultimate provocative thought we want to leave you with is this. If complexity, not curvature, is the dividing line in the universe, perhaps we need to completely redefine where we look for quantum gravity effects.
Maybe the most complex objects we can create in a lab, or even the highly complex data storage systems in our computers, also abide by quantum rules that differ slightly from the simple classical equations.
Simply because of their information density. That's a quantum rabbit hole that extends far, far beyond the stars.
Thank you for joining us for the deep dive.
We'll see you next time.